Thank you, Hashim. Now, just make sure you can all see the presentation. Is that all clear now, Hashim? Is the presentation up? First slide. Can you hear me, Hashim? Is that okay?
Yes, Terry, I can hear you, and we can see your first slide. You're good to go.
Okay. Well, thank you. And good morning, everybody. I recognise a few familiar names that have joined into this presentation, and I welcome you all, and hopefully we catch up again soon. I won't see, if you have any questions during this presentation, I won't get to see them till the end. So unlike a normal talk that I might do where I can take questions along the way, I won't be able to do that at the end. So I'll continue through this short presentation and then take the questions at the end. So it is a bit interesting at this time doing a talk, not being able to see people face to face, but yes, it should be good fun. So where does it all start? I've got the slide here, and I'll talk through where I want to go for the day. Basically, as I say here, everything in our industrial world has a designed life. The engineers know the load conditions, the speeds, the temperature, the duty cycles that equipment requires, and they design things with a theoretical life, and it's based around the operational conditions and the physical properties of the components and the required maintenance that's required along the way. So they should have a good idea when equipment is purchased at an OEM level, how long everything should last. But our reality out there is a little bit different. We all know some equipment lasts a lot longer than it was designed to, and it just seems to go forever and can be very trouble-free. There's other equipment that it lasts as it was intended to last, and we're quite happy with that. The design is what we expect, and we get a good outcome. However, we get a lot of equipment that's got a shorter life. It doesn't last anywhere near its design life, and that is a lot of our reality. Some equipment as well, we'll notice, seems to have reducing life. The first time it gets installed, it seems to be that was its longest life. And every time we repair it after that, the time between repairs, between failures seems to get shorter and shorter, and it never seems to perform as well as it did in the first place. And then we get other equipment, and it's just got a variable life. Sometimes it lasts a long time, sometimes it's a short time. The lifespan between failures or urgent repairs can be intermittent. So we get a whole range of realities. And I'll say there at the bottom of the slide, look, wouldn't we be happy if we could just get the design life from the equipment? If we could just get what it was supposed to get, we'd actually really be quite happy. And that's really all we're asking for here. We just want to get what we are supposed to get in the first place. Now, a little bit of theory here. Some of you might have seen this, that we talk about this when we do our level 2 asset reliability course, but I'll just give a bit of background here about reliability, just to give it a bit of a definition for those that aren't really familiar with it. It's a bit like that word sustainability. It all depends on who you're talking to, what it means. So reliability, this definition here, is most commonly referred to as a probability that the equipment or process can operate without failure for a period of time under certain conditions. So in this case here, if you can see my mouse from T0 to T1, it's meant to go for a period of time. If it fails before then, okay, or needs repair, we can work out what its reliability actually is. Now, reliability can be a number, and there's a definition here, be a number between 0 and 1 or a percentage. And that is the probability that it can go from one period of time to the next period of time. Now, if we know an equipment's mean time between failure, that's what this MTBF is here, we can work out its failure rate. And in that equation, we've got lambda. If we know a time frame that it's meant to last for, we can work out how reliable something should be. Okay? Now, the longer the T1 is, the longer the time frame is that it's meant to last, okay? The longer that period goes, the less reliable something comes. So just to put a bit of a definition around it, reliability can be expressed as a number in terms of the probability of it failing or not failing. Now, there's other ways we can look at that. There's other definitions that are quite similar. We could say, I've got 4 here, for instance. We could say that reliability is something that it's fit for a specific purpose for a period of time. So if it's fit for purpose and it can last a period of time, well, we say it's reliable. Reliability can also be defined as the capacity of, one item or a whole population of items or whole population of bits of equipment to perform as required over time. So we can talk about reliability in terms of one item or a whole bunch of items. It can also be said it's the continued acceptable performance over a period of time, i.e. non-failure. If something performs acceptably, we say it's reliable. Or we also, in common language, we look at it as durability. How durable is it over time? Now, in all cases, what I want to get at here is just put things in context. We always consider reliability in the context of time. Now, you might have thought of that before, but if you think about anything, any bit of equipment you've got at home or at work or anywhere that's reliable, it's always related to in a time frame. Something isn't, you don't expect something to be reliable forever, but within the time that we want it to work, that's how we define reliability. So the inverse is, if something doesn't meet our expectations in terms of operational time before it fails or before we need to repair it, then we consider that thing unreliable. If it doesn't meet our expectations in terms of performance over a period of time, we think it's unreliable. That's just to put a bit of a boundary around where we're going to go with this discussion today. Because we're talking about things that aren't reliable. We want to get them back to where they should be. So, if reliability is essentially by design, okay, essentially at the design stage, how reliable something should be, it is really defined then by the designer, by the equipment they choose, by the processes, by the materials they use, by all the parameters they use in their design. It really should be determined then. Then that means then that unreliability is caused by one or more events that influence that bit of equipment to underperform during that period of time. So reliability is underperformance to our expectations. So for this discussion, we're going to define events in terms of equipment and operational assets as anything that can cause reduction in the design or the potential reliability of equipment or process. That could be a physical defect in that sense, or it could be an inappropriate process or a procedure or something that's not done. So things that cause the equipment not to meet its reliable targets. So finding and fixing all these sources of unreliability or reliability problems, it's often called defect elimination. We talk about eliminating defects. Okay? So in this case, we're looking at these defects as events. They're not necessarily physical. They might be process related as well. And we're going to look at 7 main areas where they come from and how these 7 areas have all got their ways of reducing equipment reliability. Because remembering, we just want the equipment to last what it was meant to in the first place. I don't think we're asking for too much. That's what we want to do. So let's look at these things. So where does it come from? We've got a picture here of a range of pumps being driven by motors. And we'll go through these 7 areas and then just flesh them out a little bit one at a time. The first area we've talked a little bit about is original design. It's got to be right in the first place. Something isn't fit for purpose. If it can't do what it's meant to do, it doesn't meet its design criteria, we're going to have problems. What we buy, what is purchased, it has a big influence. If it doesn't meet the original design criteria, or later on if we buy spare parts that don't meet it, we will be reducing our ability to meet our reliability performance targets. The condition that we keep spares in to repair equipment, to replace parts, we'll see is critical in maintaining reliability. External repairers, equipment we send out to be overhauled by third parties, that can be a source of unreliability. How we install the equipment, another source of unreliability. How we maintain it, and then we'll look at finally how we operate it. So that's our 7 areas that we'll cover this morning. So first of all, the original design. Your equipment should deliver what it was designed to do. If it doesn't meet your reliability expectations for some reason, if it cannot meet it, it's not possible, then that design needs to be changed. In some instances, you might have to change your whole system if it underperforms, a piece of OEM equipment that doesn't do the job, or you might want to go down to the component level. There might be components that are causing unreliability. Sometimes it's possible. Sometimes you can upgrade, you can make modifications to assemblies, to processes. You might need to get CapEx approval. There might be things you can do within your own area of influence. That's good if you can do that. However, sometimes you'll probably have come across these where it's just not viable. You've got a design, you've got a piece of equipment, a piece of plant that's been delivered, could be new or secondhand, whatever. The company hasn't got the money or doesn't want to, and you just have to live with what you've got. You just have to live with some unreliable equipment that's not fit for purpose. I'm sure you've all come across those situations. That's just life. We just have to suck it up and do it. However, in most cases, we just want to get the reliability that it's supposed to have in the first place. Okay? And it starts at the design. The design has to be suitable initially. If it is, okay, then we look at all the other factors. So the second thing we want to look at is procurement. The purchasing of the equipment, both originally, design and project engineers can come up with specifications, and at procurement time, someone can make the decision, we're running a bit tight on budget, we've got to cut some costs somewhere. Okay, let's find the cheapest source of that bit of equipment that we can get it where we can get it manufactured or fabricated or purchased. Now, if it doesn't meet the original specifications in terms of performance, we're going to have trouble. And then if parts and equipment are purchased later on by our supply people and they do not meet or exceed the OEM specifications, the original equipment manufacturer specifications, then the components or equipment is unlikely to deliver the design reliability. Purchasing goes off and buys parts that are substandard, unsuitable. We won't get what reliability we expect. So the question there for us all is, do you get what is required from your procurement people based on some specifications that ensure reliability, or is outside of your control? If it's outside your control and others are making those decisions in isolations, it's likely you're going to have problems. And maybe some of you've seen that in the past. So, a few questions there. Are the purchasing decisions that procurement make, are they based on what we would call a total cost of ownership, not just a purchase cost, but the life cycle cost of the equipment and reliability? Or do they buy a minimum standard at the lowest possible purchase cost? The two aren't compatible. Do those who buy equipment and spares report to maintenance, or do they report to a finance department? That can greatly affect the reliability outcomes of what is purchased. What's purchased is purchased based around what's best for the company in terms of life cycle, maintainability, and reliability. We'll get a good outcome. If people making the purchasing decisions don't do that, and then there can be trade-off between price and reliability. We could end up with saving money initially, but costing us money down the track in terms of lost production and maintenance costs if we forfeit reliability. So buying based on cost alone doesn't mean the lowest cost isn't the best. Sometimes it can be, but if cost is the driving consideration, there's no doubt that leaves the door open for you to have products purchased, stored, that are going to reduce reliability of your equipment. So, bottom line there, procurement should purchase equipment and spares that maintenance reliability personnel require in the most economical way. The goal should be, you should be able to tell them what you want. Let them go and buy it economically. Let them work out the terms of purchase, the financial conditions of sale. All of that thing is what they're good at doing. But our role in maintenance reliability is to be able to come up with the specifications of what to buy, where to, where from, how much let them work all that out. Okay. The next area I want to consider is the spares that we purchase. Once we've purchased the spares, okay, they need to be kept in as new condition. Okay? A maintenance department's costs are really made up of really two big items. The labour cost of personnel, contractors and employees doing the work, man hours working on equipment, and then there's the parts that they use, replacement parts. They shouldn't be corroded, rusty, dirty. You know, there shouldn't be boxes on the shelf open. Things shouldn't be unlabeled. You know, if there's rubbish in the store that's unsuitable for use, it should be thrown out. Incorrect parts that aren't like new, they're defective. They should be treated as defective, and they're a source of unreliability. We want to be able to maintain and overhaul equipment like new. If our parts aren't like new, we're wasting our time. It's a complete waste of time. We should throw them away. The stores have to keep everything in good condition. Stores should be clean. Okay, everything should be in its place. 5S principles should apply. We'll talk about it in a minute. If you were to go and visit any of your suppliers' warehouses where they store the parts and the spares that they deliver to you, I'm sure you would find them in very good condition, more like this picture on the right. You would find their stores to be clean, things packaged, labelled well, easy to locate, not covered in dirt, clean, because they want to deliver it to you in good condition. So when you get it, when we get it at our stores, whether it's on an industrial site, a mining operation, wherever it might be, we want to keep them in great condition as well. We want to be able to open them up as if they're new. We don't want to have to reuse stuff that's going to deteriorate our reliability. So the 5S principle, some of you would have come across this, particularly if you've been through any business improvement or lean production process improvements. It's basically this. It's a great process. It comes from 5 Japanese words, okay, which I won't repeat. But the first thing is we sort everything out. We get rid of stuff that we don't use anymore, obsolete stuff. Okay, we put things that we use most frequently closest to where we can get them, and we don't hold on to things that haven't been used for years and years. We sort it out, we throw away the rubbish. Stabilize the situation where everything has a place, everything's labelled, everything has its right spot. We get that under control. We keep it clean, clean the place up, find ways of keeping out dust and dirt, doing that on a regular basis. We standardise our procedures of goods in, goods out, where things get held. If we're going to be having certain kits where we store those, and then we sustain it, we audit it. We get someone independent to audit our stores on a frequent basis to pick up anomalies, and so we keep the circle of improvement happening. We don't do it once, we keep doing it, because we want to make sure that what we get is like a store. It's new, it's clean, it hasn't gone past its use-by date. And a lot of suppliers are good at helping you. If you haven't done this before, suppliers are a great source of this. They can come in and check out what products they supply you. They can tell you what should be thrown out, what should be kept, how to store it a bit better. They might have better labelling process for you. There's lots of help you can get with this, but it's a great place to start. Otherwise, we're going to get spare parts, coming back up to here. We're going to get parts that look like this, that are crappy, that shouldn't be put into service. Not if we want to reduce unreliability. Okay, the next area we want to look at is external repairers. Now, nearly everybody sends things out for repair externally. You don't do it all yourself. Hydraulics, gearboxes, motors, pumps. It could be all sorts of machining, balancing. There's all sorts of things you send out. Okay, fans. Now, I just want to bring the question up here. How well do we manage that? We need them. We want our contractors, our external repairers, to do at least as good a job as we can, if not better than we can. Probably we're sending it out because we want them to do a better job than we can do ourselves. Otherwise, we'd be doing it ourselves. We'd have our own workshops. But how do you know? How do you know what they're doing? How do you know if they're doing a better job? If we just send things out with an expectation that they're going to be doing a precision, fantastic job. Well, we might be wrong. Okay, we have to know what they do. We have to consider what tests we want our external repairers to do. I've got some questions here. Do you specify what you require to be done, or is it left to the repairer to decide? If you send out an electric motor, you send it out and say overhaul, rewind, but what test do you want done? You know, do you want it painted to your own specification? What bearings do you want in it? What grease do you want used? They see there's some gearboxes being load tested with temperature sensors and vibration sensors on them. So when the gearbox is overhauled, there's a test sheets can go with it that you'll know 100% that there's no bearing damage, that it can handle the conditions, that everything's been assembled with precision. Okay? Specified. Ask for it, you can get it. So you have every right to specify what components you want. You might want particular brands of bearings or lubricants or materials. You can specify that. You can ask for quality assurance checks. Do they do dimensional conformity checks? Do you ask them for any improvements? When we send things to repair, suppliers might know of better, newer materials or newer seals or replacement parts that might actually improve what you send to them. They can be a great source of information if we ask them as well. And finally, have you visited your external repairers' workshops to see for yourself what they do? It's worth following a bit of equipment through the workshop. What do you actually do when we send it? How do you manage it? How do you control the quality? Who works on it? Have we got skilled tradesmen? What specifications are you repairing to? Do you have the OEM's repair manuals, or are you going from what you know? How do you know that what you're doing is best practice? Worth asking questions. And if you don't have any specifications, ask them what they do, and then start using their repair procedures to build up your own specification sheet so you can then put it out to maybe other people. And what I've heard from people that visit workshops, the mere fact that you're going to visit external repairer puts them on notice that you're interested in what they're doing. Okay? You want your job to be the best. You don't want to have them doing a better job for somebody else and not for you. So it's very worthwhile checking out what they do, because at the end of the day, what are we looking for? We want to be able to send our equipment to be overhauled and repaired, and we want to get it back as close as possible to perfect condition, as close as possible to new that we can get. No point having something come back from repair and having some parts in it like new and some parts not. We are only going to get reduced reliability. So remembering what this is about, we're about eliminating the sources that could cause our equipment not to last what it's designed to do. So we want our repairers to bring it back to an as new state. Over here on the right, I've got a fan being balanced. Similarly, if we send things out to be balanced, we need specifications. What standard do we want it balanced to? On our training course, we talk about trying to get to a G1 balance standard. We want the best balance we can get. If a supplier says, oh, that's going to take a bit more work, we're going to have to spend another couple of hours on that. Well, so what? Let's do it. We want the best we can get. We want precision. Next thing is acceptance testing at suppliers' workshops. I don't know how many of you do that. Acceptance testing is a process whereby we don't basically accept the equipment unless it passes certain tests. If we've got those tests that can be done, the best place to get it done is at the external repairers. It's no good getting equipment repaired, send it back to your site, having it installed, and then doing acceptance testing and installation and finding out that you've got a problem. The job could have been repaired recently, could have been sitting in the store for months. The best place to get it done is at the external repairers before it gets shipped to you, whether that's critical measurement checks, temperature checks, you might get electrical tests, vibration analysis, a whole range of tests you might want done, load tests. Try and get it done before you receive it. And then the next step is we want to make sure that when they send it to us, that we get it like new. We want to specify shipping and handling procedures, if possible, to reduce the risk of damage during transport. Here's a fairly common case here on this slide I've got. I've got an electric motor here. I've got the rotor on a shaft sitting on a couple of bearings. If this isn't strapped down and that rotor can rattle around and vibrate during transport, we get this effect that's called false Brunelling, where the rollers of the bearing make a mark on the raceway, and in effect we've got a damaged bearing from the day we started. Why this happens is there's no lubricant film in there, there's no rotation happening, just a bearing roller sliding, and in roller bearings, the rollers, the balls or the rollers are always harder than the raceway, so the rollers mark the raceway. Now, to prevent that, there's a couple of methods here. There's a couple of various shaft locks. There's a shaft lock here on the left that basically bends the shaft a little bit, puts a bit of a bending moment on the shaft and locks it in place, or the one on the right that locks it in a horizontal direction. Both work well. They stop the shaft from rotating. And in this case over here on the right, we've got a plastic wrap around the motor on the pallet, so when it gets shipped, it's not going to be damaged. It's not unusual for a greenfield site where a new plant's been built and they have a lot of electric motors being delivered to the site to have 20, 30% of motors damaged in this way before the plant even starts up. It's quite common when equipment has to be transported for long distances. Other things to consider when you get things shipped from external suppliers. In this case here, we've got looks like could be a rock breaker arm or hydraulic arm. That's what it looks like in the workshop on its own skid, so they can be lifted well without damage, wrapped up, shrink wrapped up, put on the back of the truck. It's probably going to be going from Perth to far up in Western Australia somewhere. This is going to greatly reduce the chance of dust and dirt and water getting into the system, into the equipment while it's being transported. If you don't ask for it, you don't get. Okay, so a few things to consider when we're looking at external suppliers. Not just the job that they do, but we want to send equipment away. We want it repaired like new. We want it to arrive back at our site like new. It might be installed straight away. It might go in the warehouse. Some things might not even go in the warehouse when we get them back. They could be sitting outside quite a long time. We want to make sure that we protect them and we don't end up installing something that has reduced reliability from the start. Okay. Next area, one of the big ones is installation. Installation errors account for a large proportion of what we call in reliability speak terminology early mortality failures. That is, it's a failure shortly after maintenance repair. The rule of thumb, maybe that's not the right word, but generally speaking, if something fails not long after it's been maintained, it's normally something to do with installation. Somebody's made an error. And there's so many ways that we can do that. Some common human errors here I've listed: not following the procedures, okay? Not using the correct tools, rushing the job, taking shortcuts, not installing with precision equipment or precision methods, having poor alignment, using the wrong parts, accepting the wrong parts, damaging parts during installation and not replacing them, just leaving them damaged, using parts that aren't like new or second-hand parts or all you can find parts, and particularly fastness, putting things in that are too tight or more commonly things that aren't tight enough. So lots of things can go wrong in installation. It is absolute critical part of reducing unreliability by putting equipment into service correctly, how it should be, all the parts that go together. And it comes down to having procedures, having training, having the right tools, and not accepting a poor job, having a culture of doing things right. Precision installation says it's particularly important for certain parts of it, certain types of equipment. Ball and roller bearings, we'll talk about that in a minute. Absolutely crucial. It's so easy to wreck bearings at installation. Shaft and mechanical seals, easy to damage seals at installation and then have leaks from there on in. Gaskets and O-rings, easy to use the wrong O-rings and gaskets and squash them and destroy them at installation. Couplings and pulleys and belts all need to be fitted with precision. Fasteners, nuts and bolts, etc. We talk a bit about this on our reliability courses. Bolts, there's only 3 options with bolts. You tighten them up too tight, you're too loose, or you get it just right. And without the right tools, getting it just right is just about impossible. And that applies for electrical connections as well. Shaft and pulley alignment, talk a bit more about that. Pipe work, foundation, bases, their stiffness and their flatness, all very critical installation. All these things, without going into detail about, what it does, they all produce problems that cause unreliability, they cause vibration, they cause early mortality failures. Very, very common problem. We've got to be very fastidious and rigorous at installation to make sure that our tradespeople understand how crucial it is to install things correctly. Here's some examples we get, with bearings. Up here we've got bearings on tapered sleeves or tapered shafts. Very, very easy for small bearings, when I mean that bearings up to maybe 100 mil. Very easy to mount them too tight so they run hot and fail quickly. Larger bearings, very easy to have them too loose. Very common on pulleys and conveyors and things to have bearings that are too loose. We want them to get just right. There's tools that can do that. These type of bearings, cylindrical roller bearings and electric motors and pumps, need great care to prevent damage during installation. This ring here slides into that outer ring of the bearing. We're talking about clearances between these two surfaces of only maybe 75, 100 microns, not a lot. Very easy to damage the bearing during installation and then have it damaged from the day it starts up. Very easy to do. We need the right tools, the right hammers and drifts if we're going to have to knock bearings on shafts, or the right heating devices to expand the inner ring of the bearing so it fits in a pipe shaft. We need to handle it with absolute care, and there's training courses available to teach people this. Otherwise, that the likelihood of bearing damage installation, I think the figures are somewhere around maybe 15 to 20% of bearings fail because of installation, and we'll see later lubrication big. So this is the starting point, but applies to anything that's installed that needs precision. Alignment, another big common issue with installation. Whenever we want shaft alignment, we want these 2 red lines. We want the center line of the driving and the driven shafts to be exactly identical. There's no way you can do it without the right tools. Very common in equipment have what we call soft foot, where one or more of the bases of the equipment, normally the motors, is not flat. So when we tighten up the machines and we bolt them down, we distort them, we put them out of alignment, and that causes reduced reliability of our bearings, our seals. It causes high vibrations. It causes other things to come loose. Just causes so many problems. Problems that are very easy to prevent, though. If every job we do, if every job is installed with precision, with alignment equipment that can check these things, we check the foundation, we check software, we can eliminate it at installation. If we don't check it, though, or do it, chances are, very high chance, we're going to have reduced reliability out of our rotating equipment, because we can't do these things by feel. We need the right tools and training. So, next thing, point 6, the maintenance strategy itself. It's interesting. Maintenance is not the biggest part of reliability as a lot of people think. We might include installation with maintenance, but the maintenance strategy itself it has to be considered, because maintenance can deliver really good work management, but it doesn't always improve reliability. Interesting thing to start. We can have a great CMS system. We can do lots of PMs. We can get the work done. We can have high PM compliance. Okay? We can have a great team of people doing a good job, but it doesn't always improve reliability. And you can see why. We've got all these other factors, and sometimes maintenance can add to the unreliability itself. So just a couple of things I'll bring up here. PMs. PMs, I'm talking about interval-based maintenance tasks when we're going to be doing intrusive maintenance, not an inspection, but a maintenance task. That should be based on equipment that has a known predictable life, and when the PM is actually going to prevent a failure. Okay, and that applies to equipment and materials that corrode, that they wear, fatigue, or they deteriorate, or they have some reduced functionality at a constant or repeatable rate. Okay, so we know it's happening. We know that it takes so many months or so many revolutions, or so many hours of production. Repeatable processes, they're fantastic for PMs. But not all PMs add value, and some we do are probably a waste of time. There's probably some that are just there for some reason. OEM said so, or historically, and they are a waste of time. So the question is, there are some tasks not doing anything to improve reliability, or they're actually causing unreliability. Because every time we do an intrusive PM, every time we repair, every time we pull something apart to replace, to do something, we have the risk of an early mortality failure every time we do that. So we have to consider whether the PMs we're doing are actually improving or doing anything. It just has to be considered. And people would call this the PM optimization program. Well worth doing if you haven't yet ventured down that path. There's a comment there at the bottom of the slide. Most maintenance repairs or replacement activity where we're pulling things apart, we're fixing them, we're restoring, we're replacing, most should be done based on its equipment's condition, not based on time or running interval PMs. We should know the condition, and that should be the basis of the maintenance, not just based on time. We're doing a lot of PMs based on time. We're probably causing a few extra problems that shouldn't be there, and we may not be doing anything to improve reliability at all. So condition monitoring is part of a maintenance strategy. It's going to help us detect a huge range of defects. We're using vibration analysis, thermal imaging, electrical motor testing, ultrasound, all these different technologies and methods. We have to have it as part of the maintenance program. It's going to help us prevent unplanned downtime. We're going to have plenty of forewarned notice of an impending problem. But in itself, it doesn't actually improve reliability. It doesn't actually do that. It's just telling us we've got a problem. We need to get to the root cause of the problem if it's not a normal end-of-life equipment event. If it's something that wouldn't be there, we've got to find out what it is. So it's interesting. I see a lot of posts that people put on LinkedIn and other forums of things they find with condition monitoring. They find defects and they can go into in great detail, and often think that's really interesting, but you haven't actually improved reliability. But you've done the detection. That's really good. But the next step, how did it happen? How are you going to prevent it? Where did it come from? It's not a natural design fault. It's not an end of life failure. It's a random failure. You've got to fix it, and that's really what we're talking about here. Trying to get to the root, proactively get to the root cause of all these things that are going to add up to make our equipment not last what it was designed to do. And one of the big ones, of course, in maintenance is lubrication contamination. And research, as I say here, suggests that it's the main killer of failures in things like bearings, gears, engines, hydraulic components, all those things that rely on a few microns of lubrication between their mating surfaces. Contamination in these instances, or the wrong viscosity lubricant, or the wrong additives, or whatever, has a massive impact on equipment life. And it's probably, in terms of reliability improvement, or the reason for unreliability, it could be the number one in a lot of industries. It could be more than installation or spare parts, when it could be that high. So the interesting thing is it's entirely preventable. Doesn't matter what your industry is, if you're in the chemical industry or water industry or mining industry, filthy, dirty environments, it doesn't matter. We can keep contaminants out, and we can keep our lubricants clean, and we can get the life that the equipment was designed to do. Now, many of you would have seen this graph taken from the ISO 44006 oil cleanliness charts. Now, Might mean anything to some of you who haven't seen it, but what it's basically saying here is if I've got here these little codes along here are oil cleanliness codes. So the lower the number, the cleaner the oil. So cleaner oil down that way. And here, the higher the number, the dirtier the oil, clean down here. If we can go one state of cleanliness, here say 2219, if we can go from this state to 1714, if we can clean up our oil, get contamination out, what this little table is saying here, we can expect quite a dramatic improvement in reliability. If we can clean our oil from this code to this code, it's saying, oh, your rolling element bearings should be getting 2.5 times the life that you're getting now. That's interesting. Your gearboxes and other equipment should be doubling their life. If it was hydraulic and diesel engine equipment, you should expect 4 times life improvement by cleaning up your oil, okay? Or another way, what it's saying is, at the moment, if you're running this grade of oil, this you might say this dirtiness of oil, for want of a better way of putting it, you're actually reducing your life by about 4 times, or your bearings 2.5 times. You've got unreliability. If you want to get rid of unreliability, clean up your oils. That's just fact. And many companies who are doing this have testified to amazing results. Finally, as we're coming up to a bit over 40 minutes, operations. How equipment is operated in the operating environment, it actually may affect reliability more than any other factor. I've mentioned lubrication is a big one, but this is huge. It all depends on, the proportion you've got of each of these operations. Here's a study from ABB in the UK. Now, I've seen similar ones from Ron Moore and other sources, and they tend to be fairly similar. What do these guys say? Operations can account for up to maybe half of all the sources of unreliability. Poorly defined procedures, ineffective teams, cross-functional teams, lack of measures, lack of training, okay, can account to 30 to 50% of unreliable plant. The assets themselves, inaccurate initial specifications, we talked about that at design, poor design for maintenance and operation, changing use of modification for aging assets can account for a fair chunk. Maintenance itself, not such a big source, not a good, we talked about strategy, maybe inadequate condition monitoring or poor or no rebuild specifications or lack of training. We've added a few more in there. These don't fit in with my 7, but maintenance accounts for a bit. But a lot of people would say operations can be one of the biggest factors. And people would say in mobile plant, that might be low. I can say that can be quite a lot higher, which is why a lot of organisations, no doubt, are going to automation of their mobile fleet to get away from the problems that operators actually cause themselves. Operators, a big source. So how it's operated has a great effect on reliability, maybe more than others. If equipment's run beyond its parameters, too fast, too slow, overloaded, cavitating, it's going to reduce life. And then if there's anomalies that go unreported, leaks, noises, ignoring alarms, overriding alarms, they all cause unreliability. High pressure hosing down can cause water ingress and cause rapid decrease in life. So operators need SOP, standard operating procedures. That's one of the critical points, so that reliability is not traded off to meet production targets. And there's repeatability, consistency of operation. We need our operators to run equipment by standard methods and try and reduce the variability of how they run equipment so that they're running it within its design parameters and take some ownership. Some of the methods that people use to do this, it's called operator asset care, operator-driven reliability. Good program operators get involved in some basic care and maintenance tasks. It can overcome a lot of those issues. They could be doing basic temperature checks or vibration checks or changing filters or cleaning equipment. It could be a whole range of things. The idea there is operators can be the frontline defence to prevent failure and help get to the root cause. They can be both the cause of problems and they can be both part of the solution. But if we leave them out of the equation, to say here, high equipment and operational reliability, it will probably never be achieved without operator involvement in prevention and detection. If we leave them out of the equation, we can get a long way down to improving unreliability, but we'll always have a gap in the process. So that we have to consider what they do to the equipment and how they can be part of the solution. So in coming to a conclusion here, we talk, where does reliability come from? We could flesh out each of these topics in more, but this is really to give you an overview. We talked about the design. Okay, that came in a bit late. Operation, procurement, spares, external repairers, installation, and of course the maintenance strategy. Okay, they're 7 areas and they have all their subgroups. So a bit of a checklist here for you to conclude. What are some of the things that you may want to consider or do? Well, at the design stage, we want to ensure reliability and maintenance get involved in new projects to influence reliability and maintainability outcomes. If we're completely divorced from what's purchased and what's designed, well, we may end up with equipment that's just not really fit for purpose. Procurement, we want to make sure we're buying the right equipment or the spares. The stores, how it's stored, we want the parts stored correct, clean, new. At installation, wow, we want to install the equipment with precision. We've got to have procedures, checklists, maybe hold points, standards, correct tools. Have alignment and balance standards for the site. Ensure fasteners have specifications on torque settings and the tools are available for people to use, and get people trained in precision installation skills. Get them trained in using the right tools and understanding that what effect that has on reliability. And then our external repairers. Look at having specifications for common external repairs, so we know what we're asking for with our motors, pumps, gearboxes, okay? Develop some transportation standards and do some acceptance testing before delivery, if possible. Maybe get suppliers to do it or send out a technical expert yourself. And with maintenance, ensure the maintenance strategy is reviewed. Eliminate unnecessary PMs that could be causing unreliability. Implement a precision loop program with oil cleanliness specifications, filtration standards and targets. And that will get rid of a lot of unreliability problems. And then finally, operators. Ensure that they're operating within standard operating procedures and the equipment is run within its limits and they have some involvement and ownership in basic care and maintenance. So there's some pointers. Maybe you're doing some of these already, maybe they're not. But hopefully you can see that unreliability can come from a lot of places. So wrapping up, if we can prevent all or most of the sources of equipment unreliability, then we're well on the way to get the design reliability. That's what we want. We're not asking for too much. We just want to get the equipment to last what it was meant to do in the first place. And the question there, hey, what would that be worth to the business? What's it worth for you to do that? I bet it's an enormous amount of money. So look, if you want to know more about some of this I teach a asset reliability practitioner category 2 course. We'll actually do 3 courses, a 1, 2, and a 3. But the 2 course is really the best one, I think, for this sort of topic. I'll wrap it up there. So look, thanks for your participation, and I'll see I close this down, and maybe we can have some question time. So I have to stop sharing that.